Thank you for having me in this meaningful conference, and sorry for making the conference late. So my name is Jae Kim from UNIST, and today I would like to talk about what we can do with solid-state quantum measures such as defect or quantum dot. So basically, they can provide very fun playground in quantum. So the quantum emitters, it is there is a variety of forms that include chemically synthesized colloid dot. Quantum dot is basically nanocrystals, and the epitaxially from quantum dots. So MV, MOCVD, it can form self or aggregate self quantum dot. Also, we can use the like MV centers. So there exists a bunch of point defect that can be used as a quantum emitter solid. So these kind of the quantum emitters, so somehow they confine, three-dimensionally confine either axon or the electrons in very small areas. So these they have discretized the energy level like the atoms. So for that reason, we call them as artificial atoms. And this discrete energy level, we can choose two levels. So these two level system can provide photonic qubit. If they have a ground state spin, we can also utilize their spin state as a spin qubit. So with the solid state quantum emitters that provide a source of spin and photonic qubit, people implement several important quantum hardware that include quantum light sources, memories, and quantum gates, and strong nonlinearity even at a level of single photons. So that is what we are doing with solid-state quantum emitters. But in conventional way, what we do, we build up this kind of homemade confocal systems using high energy system and detectors and lasers. And so we spatially map these samples and spatially and spectrally isolate individual detectors. Then we can address their single photons and their single spin as well. So that is what we typically do with solid-state quantum emitters. So since we do initialize these emitters and optically and manipulate, read out their optical signals, and also create entanglement using photons, having a good optical interface is pretty important in this field. So, but unfortunately, solid state, the host medium usually has a high refractive index that limit light extractions. So only few percent, like 1 or 2% of light can escape out. And even they escape out, the Fawcett pattern, if their Fawcett pattern is not Gaussian light, the collecting those photons will be limited a lot. And also we probably want the fast relatively combinations. That is important not only for fast the high frequency synchronous generation and also the high quantum efficiency. So quantum efficiency is competition between relative and non-negative recombination processes. So this field, solid-state quantum emitter field, spend lots of time to improve their performance. And integrating this emitter with a variety of nanophotonics was the one effort. So that includes micropillar or photonic crystals and those kind of bullseye-like structures. Having these nanophotonic structures, we can effectively increase the extraction efficiencies and deform the Fawcett patterns, not like this, but more Gaussian lights, and enhance the negative recombination time, and using the Pascal effect. Not only this improving the efficiency, it is also possible to add quantum functionality like the single photon nonlinearity by introducing cavity, a strong interaction between cavity and emitters. So that is so what this field do. And in our group, we do lots of similar work with fabricating all these nanophotonic structures, like these cavities, having this is circular gravity gratings, but consists of not rings but holes. Hole give us very nice advantages. I might have not enough time to explain the detail, but basically it has a better performance than ring-based circular regulators. So in terms of like extraction efficiencies, so they can generate the single photon into vertical direction. These red curve represent the light extraction with work, but this blue curve represent light extraction with this circular grading structures. So as you can see here, directionality improved a lot. So as a result, we can easily achieve very bright the single quantum emitter signal like the low temperature PL measurements. And also the pulsate enhancement occurs without cavity and with cavity. So this is basically how we can improve the optical performance of single emitters. And eventually we can generate single photons with high purity and high brightness and high replication rate. That is nice. But what we want here is, so quantum emitter can provide single photons, and the axion by axion cascade process can also generate photon pairs. And if they have a charged ground state spin, we can utilize quantum memory and cavity. We can create spin photon interfaces. They are all important quantum researches. But what we usually do is we do this kind of experiment on optical tables. So eventually, obviously, the next step will be integrating this kind of emitter in more realistic photonic platform like photonic integrated circuit and optical fibers. And such integration requires hybrid integration or heterogeneous integration technique between dissimilar platforms. Usually, the emitter can be formed like gallium arsenide or the diamond or the gallium nitride, some active medium widely in photonic platform. They like the silicon or silicon nitride or lithium niobate. So somehow we need to integrate these in the platform. And there is lots of different techniques. You can, if your emitter is not particle, you can just disperse them, or you can epitaxially grow the two different material or wafer bonding techniques. But eventually, the transfer printing or pick and place technique is pretty nice for quantum photonics. So this is one example how we can integrate the quantum emitter into silicon photonics. So this is what we did 10 years ago. So this is the FIB, and the micro tip can pick it up, and basically we can transfer the emitter anywhere we can put on. So
what is the emitter made of?
The indium arsenide, gallium arsenide. So indium arsenide quantum dot on gallium arsenide, actually indium phosphide host medium.
Just a kind of triangular shaped quantum dots.
Not triangular, the hexagonal, both hexagonal. So this is the nanobeam structures. So this nanobeam structure, the quantum dot is inside. So single photon generated on this indium phosphide nanobeam can be transferred onto silicon waveguide nicely. So, and we can also perform simple underground twist measurement on chips. So this is kind of simple demonstration of hybrid quantum photonics. So we can integrate the emitters, and this field developed lots of method to even integrate the spoken nanowire detectors and strong nonlinearity and manipulation of photons and the linear nonlinear interaction on the chips. So basically, this will be kind of dream of this hybrid quantum photonic system. From generation and up to detection, everything or every operation occur in a single chip. That will be very fascinating work. But today I would like to more focus on the hybrid detection with fiber optics. This is also very fun, and there's lots of things we can do. So this shows the left panel shows an image of array of quantum emitters. So this is indium arsenide, indium arsenide, indium phosphide, the quantum dot that emit telecom wavelengths. So not in this case, not the microgroup. We made a microstem that is routinely used for 2D materials communities. So made by PDMS, and with that microstem, we can pick it up. So just push and take it out. Then we can selectively take out one single quantum devices. Then using this kind of pattern transfer system, we can place our quantum emitters at the core of single mode fiber. So this red light is a laser from the opposite end of fiber. So that guide or where we should place our emitters. So with this technique, we can align our single quantum emitter very well onto single mode fiber, and basically that enable plug and play type single photon sources. So our emitters here, and single photon can come out through the fibers. So from the simulations, we could simulate the single photon coupling efficiency into single mode fiber over 50%. But in experiment, we achieve this actual single photon coupling efficiency around 10 to 20. So with this, the fiber integrated quantum emitter, we can implement all fiber connectorized quantum system. The lasers, the emitters, all the filters and detectors, they are all fiber connectorized. You can just connect all the fiber parts, then you can get the single photon emission at the end of fibers. And the most important advantage here is there is no alignment stuff here. So there is no alignment loss over time, so you can maintain the high stability few hours, few days, even the several thermal cycling process, the intensity doesn't decrease with time. That is very strong advantage. So not only single photon generation, we can check whether they emit in the single photon or not. That is important to implement more advanced quantum photonic applications. So in the case of distinction single photons, when you send two photons on a 50-50 beam splitters, these four events occur while you have two indistinct single photons. These two events destructively interfere, so two photons always leave together. Then you can confirm our emitters indeed so generate the antibody event. So we can confirm that this event doesn't occur with our emitters, depending on their photon polarization. So when parallel polarization, which is in distinction case, the orthogonal polarization, which is a distinction case, you can see the difference here. So it is nice since we can advance all fiber connectorized quantum systems. So next step is clear. Then we can make the system more scalable. So in previous way, there are lots of approaches to make fiber integrate single quantum sources like this. So they approach the fiber to the kind of chip including single photon emitters and gluing these fibers. And also here there's a glue stuff and some gluings. These are all the chip to fiber integration. So with this kind of integrations, it is very difficult to guarantee scalability. And this is not chip to fiber integration. This is single device to single fiber integration with diabetic couplings. This is very nice. So they can achieve very high coupling efficiencies and do not waste the samples. But these are the advantages. This is the mechanical stability is very low. It is very fragile to handle this system. But our approach is this is also the previous chip to fiber approaches is indeed many they can consider to make array of quantum emitter and bring this fiber array like this or like this. work like this. But since the randomness of solicited quantum emitters, even do this kind of scalable approaches, getting high yield when you forms, it is very low. Yeah, the yield will be very low. So, but in our case, the approaches, they provide not chip to fiber integration, but single device to fiber integration. So we can easily achieve multi-channel the quantum devices. This is with fiber we can integrate 4 different the emitter shears. So in the, again, our membrane has a nice the circular break rating structures, so that it emits single photon with high directionality, so they can provide bright single photons, and we have some kind of gate. Later we would like to apply the electric field to tune the frequencies. So eventually this when you choose the 3 bright quantum dot and integrate them onto channel 1, 2, 3, we could achieve this kind of nice the single photon dot signal and single photon signal from there. But the most important advantage here is since this is not chip to fiber integration but single device to fiber integration, we can perform pre-characterizations and post selections. So also our approaches do not make any change in their optical properties. So before integration is black, and after fiber integration is red. They have the identical PLS spectrums. That is possible since our cavity structure is membrane. Also, the whole base structures provide more interconnected design than ring structures. The ring structure is very sensitive to external strain. So when they are integrated onto a heterogeneous platform, it induce a frequency shift, while our full structures, they are not. So with this advantage, we selectively choose another single quantum emitter, and we having the similar frequencies, and add that onto port 4. And indeed, after integration, they maintain the similar single photon emission at the similar wavelength. But there will be small amount of we cannot control. For that, we made some kind of electric gate, and that apply the electric field, and we can make the device tuned by applying voltage. The amount of frequency shift is not that great in these times, but this, as a proof of concept, we found that kind of work well.
So the reason that you can shift this energy is basically strain induced by the gate field, or that?
No, it's actually kind of such. Yes.
Yeah. By the way, so here that where the single photon emitters are located, it was
inside the emitters inside the middle.
So you didn't put anything to the top or the inside it.
Yes.
Yeah. So which means that you know that where the single photon is.
Yes.
The nanocrystal is near wafer.
Actually, we Indimasan self-assembly Indimasan quantum dot.
It's a random.
Yes, it's just random. So we basically create like a few hundred of them, then just create as a bright one.
Then kind of find the bright one, which
Yes.
is tend to be then contains that single photon.
Right. So that is randomly the bright one usually it means that they are spectrally specially coupled with cavity well. So we expect that means somewhere in the middle with the emission frequency.
What is the typical density of this?
So yeah, that's important. So in this some group prefer to use low density, like only one quantum dot within the 10 micron. That is pretty low density one. So with that sample, we can do pre-characterize the position ends. We can do second e-beam accelerated stuff to especially maximum one. So, but our approach is kind of we have like few tens of quantum dot in a 1 micron size. So quantum is always there.
Which means that there is danger that you may not have one single photon. That's true.
One good thing is each quantum dot have frequencies. So with that, we also need spectrally filtering out. So even we have few tens of quantum dots coupled with a cavity in a single devices, that's okay. They may have all different frequencies. So anyway, we can selectively filtering out single quantum. So these frequency tunings. So that but quantum emitter can be a good source of single photon, but simultaneously there can be a mediator of interaction of photon and photon or spin and photons. So like there's a lots of examples. So the quantum emitter at the middle of the waveguide, they can be used as a photon number filters or the few photon phase shifters or the integral photon generation via two photon spectrum. So the role of quantum emitter here is not single photon source, kind of the mediator at the level of single photons. So having this emitter at the middle of propagating photons will be very important. But so far, the five integrated quantum light sources only has a lot of single sources. To do the similar, to have the similar, somehow we need to have our emitter at the middle of two fibers. Then this can be a mediator of the propagating photons. And with this concept, it could be possible to implement classical two quantum channel inverter with the emitter at the centers, or the single photon nonlinear interface and spin the quantum memory stuff with the propagation of photons. To realize this concept, we are developing the similar approach with the fiber and integration, but now we have not only this part, we have another fiber part to something like that. So now we have two fibers and our emitter is at the middle of the two fibers. And this is kind of understandable or not. So indeed it worked very well. So this is reflection is the left fibers and transmission is the right fiber. There is a laser stuff with the 10 to 90 pin splitters. So laser extension rate comes something like that, and reflection fiber code the other way. So you can see the reflection transmission both channel work well. So this here at the middle of fibers that can provide single photon in both sides. But eventually, what we would like to do with this concept is not single sources, but kind of quantum mediators that mediate interaction between photon and photons. That will be very nice. So let me briefly summary the work we did so far. So the goal of these studies and quantum emitter can more efficiently interface and connected to each other, like with these fibers systems, plug and play operations, and scalable multi-channel operations, and inline quantum systems. So this kind of file-based quantum devices will be very useful variety of application that includes QKD or the long-distance quantum interference or photon-based quantum simulation and entanglement distributions. Those kind of things is the what we'd like to do with our approaches. And with this field, every group has their own unique approaches. Like Spell Quantums in Denmark, they prefer to use this kind of photonic crystals. Candela in France, and they prefer this kind of nanopilla-like stuff. But in our room, we prefer to use these CBD structures and device to fiber integration stuff. So this is each approach has their own pros and cons. But eventually, the common goal here is advancing our quantum research further to be more fit with quantum photonic applications. So this is the summary of my work. But not only this work, we do lots of ongoing work with defect in crystal, like quantum sensor stuff. This is HBN. HBN has a spin qubit, so similar cavity and similar interaction technique can be used with HBN, and it is possible to measure the ODMR through the optical signals through the fibers, and we have made this kind of HBN fiber integrated HBN quantum sensors and measure the thickness of the metals that stream the magnetic field. So with the change in the ODMR shift, we can estimate the thickness of metals. That is pretty nice. Previously, there is a classical thickness gauge using ultrasound that require touching the material, but this kind of quantum sensor can measure the thickness in a remote way without touching the materials. And also not only single quantum emitters, having multiple quantum emitter in a cavity can bring the collective effect. So we do study super radiance or some radiance phenomena in a multi-emitter in a cavity systems. So in this case, we studied some radiance that yield very strong bunching emissions only with two coupled emitter in a cavities. And also recently we do collaborate with groups who are expert in the atomic gas. So we try to make hybrid quantum system between artificial atoms and atomic natures, and they can interact via the photons. So this photon interference can mediate the interaction between natural atoms and artificial atoms. So that require matching the wavelengths of the atomic system and the system. We do advancing this kind of work. So this is the last slide. So this is group members in my group, and all this work, I'd like to thank the collaborator for the work I presented today. Yeah, thank you.
Thank you for your nice talk. Any question?
Those quantum emitters, they probably got certain distribution of direction of emission because of the molecular fields. Then you have your cavity mode, which needs to be probably somehow aligned with that emission. But then you have your fiber modes as well, which not necessarily align with the cavity mode. So you have 3 degrees of freedom. Mm-hmm. You cannot control all of them.
Yeah, actually, that is important. That fully depends on what kind of emitter I use, like the quantum dot I use first.
Like what kind of emitter.
Basically, I know the starting point. I know that not
for boron nitride. I don't think people even know what was the.
So yeah, it depends on the emitter. Like Injumas and C5 quantum emitter, they have in-plane polarizations, and they can. This kind of membrane cavity can support T mode like the mode, so they can effectively couple with the in-plane quantum dot and the in-plane, but we do not know which orientation they will have. But our cavity has they can support any direction of in-plane depolarization, so it is okay. But why depending on the silicon vacancy in silicon carbide, if their dipole is vertically oriented, that kind of dipole is hard to couple with this kind of membrane cavity. So yeah, it is important to consider dipole orientation of emitters, and we need to consider that dipole orientation, whether that dipole can be effectively coupled with cavity or not.
So then the last part you showed when this the super radius and then this bunching, was it just the two quantum dot accidentally located?
Yeah, accidentally.
So it was not you deliberately create this.
No.
Yeah. But assuming that again that if you just use the higher density of the quantum dot, you may have even just more than 2 and 3.
Yeah.
Yeah. And you may have even larger superradius behavior can be.
Actually, this is similar to super radius, but actually super radius behavior usually the G2 bunching remain to less than 2, but this kind of high bunching is a signature of some radiance state. So yeah, high density quantum dot can be useful to have a multiple quantum emitter in resonance, but eventually that is pretty difficult to control all their. That all rely on the random process, so that is not an ideal way. So these days people try to make the waveguide and later low density samples, so we know the multiple quantum emitter coupled with the waveguide. Then those waveguide with a fast separation like few micron, then they can make an electron node individually. Then they can intentionally make them in resonance. Yes. That's more controlled way.
Great student of some really appreciate taking on all you. I had a question about it's like I just studied in university directional emitted light is random.
Yeah, library has a donor-like buffet patterns.
As I can see, the structure of quantum emitter in this experiment is upward and downward direction quantum light. Then how can we extract the downward direction?
So, but yeah, you are right. Anyway, the membrane, we due to the cavity we integrated that enabled our dipole emit the photon with a directional wave. But that directionality means it can go both directions, this and that. So in this case, we can couple both directions with both fibers, so that is okay. But the previous wave, like this. So yeah, the photon can couple effectively with this direction, but there will be another photon in opposite direction. But usually we have a metal plate that provide reflectors. So the photon comes out these directions, can reflect it back and couple again with the fiber. But yeah, that require very precise control of distance of these reflectors.
Additionally, if we use hyperbolic structure or any analytic structure to opposite direction, then
those kind of thing will work. Yeah.
Yeah. Then is it work as a good quantum raising the good quantum efficiency?
Yeah, that will definitely work. Having more designed photon structure for reflect back the structures that will work. But the only problem is difficult to make. Is very difficult to make and align them where is quite a burden of the experimentalist. Yes.
Yeah, okay, yeah, let's provide a big applause for Vice President.